that is the world's first nuclear-powered interplanetary spacecraft. Or it will be, if the United States can complete an insanely ambitious engineering timeline. And even if they do, that fission reactor out there won't be your typical sci-fi fare.
Why are you holding a guitar?
Don't worry, Aria. This is just my science to American translation device. You'll get it.
Now entering the facility.
We're hard at work here at the facility because just weeks ago, the United States announced that it wants to close a 60-year gap in American space power of the nuclear variety. That's right, in just 31 months as I'm filming this video, the United States wants to put a nuclear-powered spacecraft on its way to Mars loaded with multiple science helicopters, or, as the Americans describe it, you gotta admit, the plan does sound like it has some of that American space exploration spirit to it. And didn't that make more sense to you with the... Yeah. The mission is currently called Space Reactor-1 Freedom, or SR-1, and its goal is to be on the way to Mars by December 2028. As NASA points out in its mission outline, nuclear is really one of the only ways to take those next small steps in space. As nuclear fuel is 1,000,000 times more energy dense than chemical fuel, it doesn't depend on waning sunlight in the outer solar system or panels covered by Martian dust, and it provides enough thrust to make sure that scientists don't spend literally their entire careers just waiting for a ship to get somewhere. But because freedom will also be uncrewed, NASA doesn't have to go all out. The plan is to use existing technology, launch as soon as astronomically feasible, and ultimately prove that U.S. nuclear will be the first to establish the transcontinental railroad of the solar system. Instead of sci-fi levels of thrust, SR-1 is going to start a little smaller, with less powerful but more proven American technology. Oh yeah. This is SR-1 Freedom as it's designed right now. As you can see, it's not your typical looking thick thruster ship, and the engineering is a lot more complicated. First and foremost, the nuclear fission reactor that will power SR-1 is right here at the front of the craft instead of at the back like you might expect. This is to account for the unique challenges of radiation. We want the reactor to be as far away from the payload as possible, time-distance shielding. Aiding this is the radiation shield, which, when right behind the reactor, creates a shadow that the whole craft can hide in. Behind the shield is where reactor heat is turned into electricity, which is routed down past the radiators, past the payload, and finally to the electric thrusters. That's right. SR-1 will be nuclear electric propulsion and not nuclear thermal propulsion. Why not use the full power of the atom and heat up some reaction mass in a fission reactor and fling it all out the back like a chemical rocket would? Well, electric propulsion is more or less proven out in this space, even if building all of it in just 31 months is unheard of. We don't know exactly what SR-1 will run on, but apparently heat to electricity will be done by a Brayton cycle heat engine. I said it was complicated, Aria. To make sense of this diagram, we're going to simply follow the fluid. Sound good?
Okay.
On the left is the fission reactor. It heats the working fluid, which moves to the heater, where heat is thermodynamically exchanged, which is to say, it's not in direct contact. Hot fluid in the second loop now moves to the turbine, which, just like fission reactors on Earth, generates the electricity. But there's still heat that needs to be lost to cool the core, so fluid flows through the recuperator, ignore that for now, to the cooler, where it exchanges heat thermodynamically again with space. Finally, fluid moves to the compressor, which gets it to the right temperature and pressure, and is then preheated in the recuperator before it all starts over again. All of that is just to create some electricity, but to power what? Ready for the next piece of technology, Aria? She's ready. This is a Hall effect thruster. This amazing machine creates thrust by accelerating ions. Here's how it works.
Oh my god.
The cathode fires electrons out like an old TV. Those electrons are drawn in towards the anode but stopped by a magnetic field. Propellant gas is released into these trapped electrons, which smack into them and ionize. Now charged, the heavy gas ions follow the electric field and are accelerated out the back of the thruster at many kilometers per second. This is the source of thrust. Finally, extra electrons at the cathode neutralize any accumulating charge on the engine. Now, I know that was a lot, but I needed to show you how complicated each system is to get across to you how difficult it's going to be to eventually combine all of these separately proven but never before combined systems, especially when there are people at NASA who don't even know the details of the mission. It'll be fine. Probably. With anything nuclear, there is of course the 800-pound glowing gorilla in the room. Safety. There is a long history of canceled and/or abandoned nuclear-powered space programs because of their apparent safety and the public's perception of their safety. It turns out that the average person doesn't want nuclear material exploding on a launch pad or over their heads. Now, you may expect someone like me to say that this perception is not quite accurate. However, I do need to say that the public is not entirely wrong here. Since the 1960s, humans have launched more nuclear reactors and radioisotope thermoelectric generators into space than you probably expected. And as you can see, a concerning number of them, most of them Russian, have either exploded or crashed or burned up in the atmosphere. Most notably, in 1977, a Soviet reconnaissance satellite powered by a uranium fission reactor, Cosmos 954, malfunctioned while trying to eject its nuclear core. Kinda cool in a Star Trek way, it then broke up over Canada, leading to Operation Morning Light, which recovered satellite fragments measuring over 5 sieverts per hour, hot enough to cause radiation sickness in just 12 minutes. Thankfully, the operation was a success. No one was hurt, and the USSR paid Canada $3 million in Oops Our Bad Slime damages. While Cosmos 954 is the most notable example, there are nuclear spacecraft that have either significantly contributed to orbital debris, spread nuclear material while vaporizing in the atmosphere, or were lost at sea. But before I start to sound like John Oliver and overly focus on a relatively small number of cases to make the general case seem more scary than it actually is, some context. The majority of the nuclear systems we've launched into space have been safely parked in graveyard orbits without issue, and we've learned a lot about securing nuclear material since the Soviet Union was rushing out 36 spy satellites in the 1960s. SR-1 Freedom's reactor won't even be turned on until it's safely in space, minimizing the amount of problematic fission products in the first place. Oh, and that lost at sea satellite? That reactor was fully intact when it was recovered, so NASA refurbished it and flew it successfully on a later mission. Yes, there has been a small, detectable, but not dangerous, increase in radiation in the atmosphere from past space accidents. But it is extremely unlikely that a modern spacecraft like SR-1 will add to this. And keep in mind that the amount of radioactivity we're talking about is much less of a health concern than just all the fossil fuels that the rockets themselves put out during rocket launches in general, okay? Context. So, with the 800-pound gorilla out of the room, I think, let's get back to Freedom. Being as complicated as it is, SR-1 Freedom wants to come together by doing things a little bit differently. Instead of building everything from scratch in the next 31 months, they want to take an already mostly built fission reactor, they want to get nuclear fuel from the United States Department of Energy, which obviously already has that, and they want to repurpose power generation from a formerly scrapped mission that already had it. This all begs the question.
You're not using that phrase correctly.
This all begs the question, why be this aggressive with a propulsion system that you could safely put your hand behind? 2 words, practicality and precedent. Well, I mean, like, don't leave your hand behind it, but according to the calculations, you could put your hand behind it and then you could say that you did that. This is why I'm not allowed in labs. Ion thrusters are among the weakest propulsion systems out there. They make just millinewtons of thrust, which is like trying to get to Mars by throwing hamsters out the back of your spaceship. Aria? Thank you. But ion systems combined with nuclear power can be crazy efficient. Just tens of kilograms of uranium-235 fuel and thousands of kilograms of propellant can be enough for an entire interplanetary journey. These engines can thrust for months instead of just minutes like with chemical rockets. And if the first nuclear spacecraft is proven out, it paves the way for even larger electrical systems to reduce the travel time to Mars from 9 months to just 2, which is going to be extremely important when the only music your crewmate brought is Aerosmith. And if all this happens in the next 31 months, NASA wants to thrust even harder.
Giggity.
And put a field-tested fission reactor on the moon as an anchor point for a sustained moon base, and then open that up to private industry. If we get lucky, this could do for space exploration what SpaceX did for spaceflight.
What? Rapidly erode democracy worldwide?
No, Aria, that's Twitter. No one at SpaceX actually, takes him seriously. You know what? Never mind. The last thing this mission can advance is less exciting, but nonetheless very important: regulation. As NASA points out, if Freedom gets off the ground, it's going to set regulatory precedent for nuclear-powered space missions, which is a non-trivial amount of red tape, and it will start creating a nuclear-powered workforce, which is hard to find and train. I think it's easy to argue that we do need more nuclear in space, so I share the sentiment of a one propulsion scientist, Jason Casabri, speaking with Science Magazine, who said, "I'll root for them. I'll buy the t-shirt. Until next time." Oh, sorry, that's science speak if you're American for this.
Now exiting the facility.
Thank you so much to the very nerdy staff here at the facility for their direct and substantial contribution to the making of this episode. If you want to join the facility, if you want to learn how to do this, if you want videos early, if you want members-only live streams, if you want all episodes of the podcast that I do with my son Adef, if you want discounts on merchandise, if you want your name in every single video, please go to patreon.com/Kyle Hill and join the facility today. And as you can see, there's so many of you. I don't know. Now, obviously, there is the elephant in the room. Where? There is the elephant in the room, which is a political one. If you asked me honestly why the current administration is trying to be super aggressive in being the first nuclear interplanetary spacecraft to Mars, it's not because necessarily, if you asked me, they believe that getting more nuclear in space is crucial to the human exploration spirit or anything like that. I think they just want to check something off on a "we did that" list, and that was us, and how cool was that? But it's good when those political motivations line up with motivations that do advance our understanding and our exploration spirit, or whatever I said. Can you tell that I do these off the top of my head? Thanks for watching.